Good morning. In the previous section, we have discussed regarding the output equation of a transformer. So, in today's lecture, we are going to discuss regarding the EMF per turn of a transformer, equation for EMF per turn of a transformer, and regarding the design of cores and the main dimensions of the transformer, and we are going to solve some examples. So, in the previous section, we have discussed the output equation of a transformer. So, we will have some uh, files here. So, these are the output equations of a transformer we are seeing. So, for the single phase transformer, it is Q is equal to 2.22 F BM delta KW AW AI 10 raised to minus 3 kV. And for the three phase transformer, it is 3.33 F BM delta KWAWAI into 10 raised to minus 3 kV. In this case, F is frequency, BM is the maximum flux density, delta is the current density, KW is window space factor, AW it is the window area. So this is AI, this is the net core area. This is for single phase and this is for three phase. So in today's lecture, we'll discuss regarding the main EMF per turn of a transformer. So before going to the EMF per turn or volt per turn equation, let us discuss the usual values of current and flux density. The value of current density, that is delta, depends on the type of cooling, natural or forced. So up to 25,000 kVA natural cooling is adopted in the practice. The current density lies between 2 and 3.2 ampere per millimeter square. Delta, whatever we have discussed, is lies between 2 to 3.2 ampere per millimeter square for natural cooling and between 5.3 to 6.4 ampere per millimeter square for the forced cooling. The flux density, whatever the BM, it lies between 1.11 and 1.4 Tesla in practice. So why we need to derive the volt per turn equation of a transformer? So again, to solve the output equation, whatever the kVA we have, that is 2.22 or 3.33 or 6.66 F delta AI BM AW KW into 10 raised to minus 3 in the output equation we derive. In this case, we are having two unknowns, that is AI and AW. AI and AW, these are the two unknowns. To calculate these particular unknowns, volt per turn equation is considered. Volt per Turn equation is considered in order to calculate AI as well as AW. So now the volt per turn equation for this purpose, consider rating of transformer per phase, that is kVA per phase, is equal to V1 I1 into 10 raised to minus 3, and that is equal to E1 I1 into 10 raised to minus 3. So finally, you can put the values of this E1. It is 4.44 pi m f T1 into I1 into 10 raised to minus 3. So this is the kVA rating of transformer per phase, kVA. Then the term, whatever the phi m is there, it is called magnetic loading, and I1 T1 is called as the electric loading. I1 T1 is called as electric loading. So the required kVA can be obtained by selecting a higher value of phi m and a lesser of I1 T1 or vice versa. So again here we are having two parameters. One is the phi m and another one is the I1 T1. I1 T1. So now phi m, it is magnetic loading, and I1 T1 is called as electric loading. So as the magnetic loading increases, what happens? The flux density and hence the core loss increases. As the magnetic loading increases, flux density and hence the core loss increases, and the efficiency of operation decreases. As the losses increase, the efficiency of operation decreases. Similarly, as the electrical loading increases, number of turns, resistance, and hence the copper loss increases. This leads to again reduced efficiency of operation. So it is clear that there is no advantage by the selection of higher values of I1 T1 or pi m. So for an economical design, they must be selected in certain proportion. Thus, in practice, we can say pi m divided by I1 T1 is a constant, that is we can say KT, it is equal to KT, or I1 T1 is equal to pi m divided by KT, pi m divided by KT. Now this is your equation number 2. This is equation number 2. This is equation number 1. Now substitute this 2 in equation number 1. What we get is kVA per phase is equal to 4.44 pi m f pi m divided by kt into 10 raised to minus 3. And finally, whatever the pi m is there, it is equal to under square root kt into kVA per phase divided by 4.44 f into 10 raised to minus 3. So simplify this. Since the EMF induced E1 is equal to 4.44 pi m f T1 is in T1 turns, voltage per turn. Finally, ET is equal to EMF per turn. ET is equal to E1 divided by T1 for the primary 4.44 pi m f is equal to 4.44. Put the value of this pi m. So this is pi m. Here it is f. So if you solve this, you get under square root 4.44 f into 10 raised to 3 into kt into kVA per phase. That is equal to, if I take this particular uh, k outside, then under square root kVA. It is k under square root kVA. So here, where k is equal to the constant 4.44 f into 10 raised to 3 into kt, it is another constant. The k is another constant. and kVA is the rated output of the transformer. The constant K depends on the type of transformer, whether it is single phase or three phase or core type or shell type, power or distribution type, or the type of factory organization, etc. Whatever the K we have got here, this K, so it is also a constant. This is the equation for EMF per turn. We can write this ET is equal to this. ET is equal to this K under square root KB. Okay. So now we will discuss the different values of K, the empirical values of K, constant. So it is uh, 1 to 1.2 for single phase shell type, 1.3 for three phase shell type, 0.75 to 0.85 for single phase core type, 0.6 to 0.7 for three phase core type, 0.45 for three phase core type. These are the different values of the K, values of the K. You can write this particular different values of K. Now we will discuss the design of core design, design of cores. So for the core type transformers, the cross section may be rectangular, square, or stepped. When the circular coils are required for distribution and power transformers, the square and stepped cores are used. So for the shell type transformer, the cross section may be rectangular. When the rectangular cores are used, the coils are also rectangular in shape. The rectangular core is suitable for small and low voltage transformers. In the core type transformer with the rectangular cores, the ratio of depth to width of the core is 1.4 to 2. 1.4. Again, in shell type transformers with the rectangular cores, the width of the center limb is 2 to 3 times the depth of the core. Depth of the So the below figure shows the cross section of different transformer cores. Different transformer cores. So this is rectangular core. This is the cross section for the square core and for the step core. This is called as the circumscribing circle. Circumscribing circle. Now, in square cores, the diameter of the circumscribing circle, the diameter of this circumscribing circle, you see, this is the diameter, sorry, circumscribing circle. So this diameter of circumscribing circle is larger than the diameter of stepped course of same area of cross section. Thus, when stepped cores are used, the length of the mean turn of winding is reduced, with a consequent reduction in both cost of copper and copper loss. However, with a larger number of steps, a large number of different size of laminations have to be used. So this results in higher labor charges for sharing and assembling the different type of laminations. So we'll discuss now the square core, design of this square core. So here it is the cross section of square core. Let this D is called as diameter of circumscribing circle. Also, it is called as diagonal of the square core. Diagonal of the square. Now, the side of this particular square is A. These are the sides of the square. Then I want diameter of circumscribing circle. This is, let us say, if I want to calculate the diameter of circumscribing circle, it will be under square root the square of two sides. If I say take this is D, so I can take the square of this A square plus A square, two sides. So if you simplify it, it is under square root 2A square. A square plus A square, it is 2A square. And that is equal to under square root 2 under square root 2 A. Root 2 A. Therefore, the side of the square is, if I want to calculate A, it is D divided by root 2. D by root 2. Then gross core area, that is AGI, AGI is equal to area of the square, that is equal to A square. If I want to calculate gross core area, I can take directly area of the square, that is A square. So what is the A square? We put the value of A here. This is D by root 2 square and it is equal to 0.5 D square. Gross core area is equal to 0.5 D square. Okay. Gross core area in case of square core is 0.5 D square. Let stacking factor is SF. This is again the constant. Stacking factor is SF. Now I want to calculate net core area. So net core area is AI. It is equal to stacking factor into gross core area, that is 0.9 is the stacking factor, it is constant, into gross core area of the square core is 0.5 D square, it is equal to 0.4 pi D square. Net core area in case of square core is 0.4 pi D square. Then area of circumscribing circle, it is pi by 4 D square. So now we'll take the ratio of net core area divided by area of circumscribing circle as net core area. You put the value of this net core area. We have calculated 0.4 pi D square divided by area of circumscribing circle, it is pi by 4 D square, and that is equal to 0.58. Then again you take one more ratio, that is gross core area divided by area of circumscribing circle. So it is 0.5 D square divided by pi by 4 D square, and that is equal to 0.64. 0.6. So another useful ratio for the design of transformer core is core area factor. Core area factor. It is very important. It is the ratio of net core area and square of the circumscribing circle. Square of the circumscribing circle. So circumscribing circle got this. Core area factor Kc is equal to net core area divided by square of circumscribing circle. So Ai divided by d square. So it is 0.4 pi d square divided by d square. That is equal to 0.4 pi. 0.4. It is core area factor. This you have to remember. Now we will go for two-stepped core for cruciform core. Two-stepped core for cruciform. In stepped cores, the dimension of the steps should be chosen, such as to occupy maximum area within a circle. Let us say this is the cross section of two-stepped core. You can draw this figure. Draw this figure. Just right siding it is uh, stepped core. Stepped core. Two-stepped core. This is your just so in the stepped core, two-stepped core, it is also called as cruciform. Cruciform core. So in this case, the length of the copper is decreases. The length of the copper decreases. The step is limited to 3 or 4. Whatever step here, it is two step. It is limited to 3 or 4, not more than that. Since we need that much different type of stamping. Yes, it is limited to only 3 to 4 since we need that much different type of stampings. So in this case, hope you completed this. In this case, let the area is length of the rectangle, B is breadth of the rectangle, and D is diameter of the circumscribing. Now, the D is diagonal of the rectangle, as I told you. Theta is the angle between the diagonal and the length of the rectangle. Now, uh, we need to calculate the AGI, that is uh, the gross core area. The gross core area. So now, in this case, what we are doing is we are having the A. This is A. This is one A, and we are having B. B. So this, in this case, from this particular figure, what we can get is here. Let us say uh, we will take this one, this part. So in this, from cos theta we can get as A by D. Cos theta will be A by D. If I take this, cos theta will be A by D, and the A is D cos theta. A is D cos theta. Sin theta is equal to B by D, and B is equal to D sin theta. d sin theta. So the two-stepped core can be divided into three rectangles. Three rectangles. The area of three rectangles gives the gross core area. If you take the area of three rectangles, it gives the gross core area. With the reference to figure, we can write AGI is equal to AB, that is first AB plus the A minus B divided by 2 into B. The third is A minus B divided by 2 into B. So if I take the area of three rectangles, it will give AB plus A minus B divided by 2B plus A minus B divided by 2A is equal to finally AB plus 2A minus B divided by 2B, and finally it is 2AB minus B square, 2AB minus B square. So in this case, if you solve this, 2AB minus B square, on substituting the value of A and B, you put the value of A and B here, you get this particular equation. So once you solve this particular, you get this thing. So now what I need to calculate is, we need to get the maximum value of theta. We need to calculate maximum value of theta. So in order to get maximum value of theta, differentiate the AGI with respect to the theta and equate it to 0. Equate it to 0. Yes, just d by d theta AGI is equal to d square cos 2 theta into 2 minus d square 2 sin theta to cos theta. So now put d by d theta AGI is equal to 0. It is equal to 0. Equate it to 0. So then you can get this particular expressions. So now we need to calculate the value of theta. We need to calculate the value of theta. So here sin 2 theta divided by cos 2 theta is equal to 2. Tan 2 theta is equal to 2. Then I need to calculate theta. So 2 theta is equal to tan inverse 2, and theta is equal to 1 by 2 tan inverse 2. It is 31.7. 31.7. So now when theta is equal to 31.72, the dimensions of the core A and B will give the maximum area for core for specified D. So now theta we put here, A is equal to D cos theta, B is equal to D sin theta. So it is 0.85 D and it is 0.53 D. Now substituting the above values of A and B, we get, again, if you take original equation of AGI, it is 2AB minus B square. If you put this 2 and this thing, you get 0.618 A square. Now again the same, that is stacking factor, it is 0.9. Now this AGI we got, net core area is AI is equal to stacking factor into gross core area, it is equal to what, 0.560. Again you take the ratio as that of the square core. These are the two ratios and the values of this particular. Now we go for multi-stepped core. That is, the step size will be equal to 3 or 4, and directly you can get the values. Now this is the different type of values. You can take this particular table. For the 3-step and 4-step, for 3-step and 4-step. So this is about the core design. Now we will see the main dimensions, overall dimensions of the transformer. So in order to have overall dimensions of the transformer, we need to consider these particular figures. This is the first figure. This is vertical cross section, and this is horizontal cross section. This is for single phase transformer. So the main dimension of the transformer are mainly the height of the window, that is HW, and width of the window, WW. The other important dimension of the transformer, width of the largest stamping, that is A, largest stamping. This is A. Here there are the stampings. You can see this particular. This width of the largest stamping, it is A. And diameter of the circumscribing circle D. And distance between the core centers D. Height of the yoke HY. Depth of the yoke DY. Overall height of the transformer frame H. And overall width of the transformer frame W. These are the other important dimensions of the transformer. So now we can see this particular, all these you can see. This is for the three-phase transformer. Three-phase transformers. This is shell type transformer. These are the overall dimensions of the transformer. Now we'll solve an example uh, which will give you the maximum information about all these parameters what we have discussed till now. Here also you can see the overall dimensions. This is for core type transformer. Overall length, overall height. Now we will solve one example. We'll see one example. Now you can take the example. Calculate the core and window areas required for 1000 kVA, 6600 bar 400 volt, 50 Hz single phase core type transformer. Assume a maximum flux density of 1.25 Weber per meter square and current density 2.5 ampere per millimeter square. Voltage per turn is equal to 30 volt. Window space factor 0.32. Window space factor 0.3. We need to calculate the core and window areas. Core and window areas. So write the given data. KVA it is given, that is 1000. Frequency 50 Hertz. Maximum flux density is given 1.25. VP is given, the primary voltage. VS is given 400 volt. Delta is given 2.5 ampere per millimeter square. Current density. ET is given EMF per turn. KW is given 0.32 and it is single phase core type transformer. Now we will calculate the particular parameters, that is core and window areas. So in order to calculate core and window areas, first you need to write the formula for window area as well as the core area. So the net area of cross section of the core is AI is equal to pi m by bm, and the window area is AW is equal to Q divided by 2.22 F BM AI KW delta into 10 raised to minus 3. These are the two particular parameters which are asked in the problem. Now I'll write EMF per turn ET is equal to 4.44 F pi m, and pi m is equal to ET by 4.44 F. Put the value 30 by 4.44 into 50 is equal to 0.1351 Weber. Flux density Bm is given by pi m by AI. Therefore, the net area of cross section of the core AI is equal to pi m by Bm, and that is equal to 0.1351 divided by 1.25, that is equal to 0.108 meter square, and that is 0.108 in 10 raised to 6 millimeter square. Then write the equation for KVA rating of transfer. Q is equal to 2.22 F BM AI KW AW delta in 10 minus 3. So from this particular I can get window area, that is AW is equal to Q divided by 2.22 F BM AI KW delta into 10 minus 3. So if you solve this, then you will get the window area, that is 0.0834 into 10 raised to 6 millimeter square. So from this we can calculate two particular parameters. So in this section we have covered the three points. One is the equation for EMF per turn. Then second is we have covered about that particular value of K and the design of course, mainly three design. The three cores we have discussed. One is the square core, then the stepped, and the multi-stepped. Then we have solved this particular example. So in the next section, we'll discuss some more examples along with the equation of that particular derivation of the no load current. So, thank you.